Okay, good day, good people. Let us look at stress and strain. Let us look at stress and strain, good people. Stress and strain is the continuity. That which we are doing here, it is the continuity from. Oh, where's my eye cursor now? Right. Stress and strain, it is the continuity from N4. Remember in N4, we said. Right. Remember in N4, we said when the material, like this test piece, it is subjected to the force applied. Whether the force applied it is tensile or the force applied it is force compression, it doesn't matter. Whether it is force compression or force tensile, we said this material will experience stress as a result of the force applied. And if we have applied the force tensile, what is force tensile? It is the force that pulls away from the object. Then the material will experience stress tensile. If the force which is applied, it is force compression, then the stress on this test piece, it will be stress compression. Now, clearly, the stress occurs as a result of the force applied. Okay, that is why the formula of calculating stress, it is force over area. If we were to cut this formula and interpret it, you would realize that it simply says stress, it is directly proportional to what, to force. That's what that formula simply means. It simply means that the stress will occur as a result of what? Of the applied force. Now, we then have to define stress based on this formula. Stress, therefore, it is the internal reaction. It's an internal reaction of a cross-sectional area. As a result of the force applied. Right. Now, what do I mean by that? When you have applied the force on this test piece, the cross-sectional area will resist or will react towards the applied force, resisting the applied force. Why is it resisting? It doesn't want to break. Why it doesn't want to break? It is because of its strength, the strength of this test piece. You know, it reacts towards the applied force, because the applied force will cause the beam or any test piece to do what? To break. Yeah? That's what we said. Now, then we said as well that when the force is being applied on this test piece, that's why we said when the force is being applied on any test piece, including that which we dealt with on static, it is exactly the same concept. It's exactly what we are dealing with, stress and strain here in N5. Okay. Now we said when the force is being applied on this test piece, this test piece will experience the change in length, The cross-sectional area as well, it will be affected, isn't it? That's what we said. Whether we apply the force tensile or the force compression, there will be a change in length and there will be a change in the cross-sectional area. Now, when the change occurs, we said it is the deformation of the material. It is what? Deformation. What is deformation? Deformation, it is your strain. Deformation, it is the strain as a result of the applied force. But before this material can experience the change, or before this material can deform, we said it that because of its strength of material, because of the strength of that material, it will first resist. That's then we plotted the stress and strain graph. We said when the force is being applied, because of the strength of that material resisting the applied force, we will then be able to calculate the strength of material using what? Young modulus, because Young modulus indicates to us the strength of the material. Then we said before the deformation occurs, from this point 0 to that dot, that region, it is governed by Hooke's law. Hooke's law gives us the picture of the resistance of the applied force, that the force applied on this test piece, it will be resisted in this region. Why? It is because of stress. It is directly proportional to what? To strain. It means they are at par. When stress takes one step, strain takes one step. It means here, when the force is being removed, the material will go back to its shape and size. That's what we said. Elasticity. We spoke about elasticity. Under that region, and that region here, we said it is called the limit of proportionality. We said it is called the limit of what? Of proportionality. Under this region, the material, it is so tough, it is so strong. The strength of its material, it gets to be shown, or it gets to show off about its strength under this region. Now, as you further apply the force, then you realize that the deformation starts to take place. The change now starts to take place up until the material fracture, breaks. Right. Then we said that region there, and this one, that one, it is upper yield, and this one, it is lower yield. Then we said under this region, your deformation starts to occur. Hooke's law, it is no longer applicable. It's no longer applicable. Hooke's law. The resistance there, it is no more. Meaning now the strain starts to perpetuate itself, starts to lead stress. Now strain is just, flowing. The deformation starts to take place. We call the upper and the lower, we call them the yield. We call them the yields. That's what we said in N4. Then we had this part here where we were able to determine the maximum stress. The maximum stress, it is determined before the fracture. We said that's where maximum stress will occur. That's what we said, good people, in N4. That's what we said. Right. The strength, the maximum stress occurs there. Now, let's look at that maximum stress there. We will go through our notes now of chapter 1. I'm just giving you the recap, and some are explaining things that you were supposed to be explained to in N4. Upper, lower, limit of proportionality. It is denoted as limit of proportionality. You then need to know what's happening under that region here. You need to know what's happening. This is upper, this is lower, maximum stress, then fracture. Because in N5, this stress and strain, you will be required as well to plot the stress and strain graph. You then need to label it. You then need to know how to explain those stages. What's happening in those stages? Remember, this graph simply interprets this material under tensile testing. Force tensile is being applied. This graph simply explains this. What's happening on this material when the force has been applied? Then we interpret the whole thing by looking at this graph. We are now able to tell the strength of this material as they've applied the force. We are able to tell that this material started to bend here. It means when force was at 50 kilonewton, then it started to do what? To bend. Then we are able to determine the stress there, the stress. We are able to determine, Young modulus, the strength of that material. Then we are able to tell the fracture point of it. This graph interprets that. Or rather, we use this graph to interpret the test that we will make on any test piece. Now, let us look at that part for a minute. When we were explaining this region here, we said the area here, it is smallest. That's what we said. It is what? Smallest. It means the maximum stress, it is calculated from the smallest area. Maximum stress, it is calculated. It will be the force applied. Which force? This force on the test piece. Whether it is the force tensile or compression, it doesn't matter. It will be that force total over area. But which area? It will be the area on that region, and of which it is the smallest area. Now, that's where your maximum stress will occur. And as well as the force total or the force applied on that test piece, it will calculate it from the smallest area. It will be stress max multiplied by area. Which area? The smallest area. Area on that region there. Area on that region there. Area on that region there. Now, let's interpret this diagram better so as to understand why we are saying it is the smallest piece there. Let's say this is your test piece and we have applied the force tensile. You'll realize that this material will elongate. Can you see that? There's a change. As you further apply, now check the areas. This area, it is quite big, and that area, it is quite small. As a result of what? Of that pulling force. Then we get what? The maximum stress. Now you can tell now that the cross-sectional area, it is small. You can tell now that the cross-sectional area now, it is what? It is small. As you further apply the force, then you realize that the cross-sectional area becomes smaller and smaller up until this material breaks. But this will be interpreted with what? Your stress and strain graph, with that graph there. Now, what is it that we know about that region? We know that the area is small, and we use that smallest area to calculate maximum stress, and we use that smallest area to calculate the force applied, or the maximum force on that test piece. Okay, that's what we said in N4. Then again in N4 we said, now the revision that I'm giving you from N4, it's exactly what you are dealing with here in N5. It's exactly what you are dealing with here in N5. Please don't make a mistake. It's exactly what you are dealing with here in N5. Okay, nothing has changed. The summary that I'm giving you, it's exactly what you are dealing with here in N5. Yeah? Okay. Now, then we had a different application of the smallest area. We were then given the compounded beam. Let's work with 3. This is unit 1, this is unit 2, this is unit 3, and the force applied, it is force tensile. Then we said this force applied, it will affect, this is L1, this is L2, this is L3. Now it means here in calculating the total length of this compounded material connected in series. Now this is the series connection. Okay. Oh, my gadgets now. Okay. This is the series connection. This is your diameter 1, D1, D2, D3. Now, if you are given a test piece like this, connected in series, because chapter 1, it deals with series connection, then chapter 2, it deals with parallel connection. Now, in calculating the total length here, it will be length total equals to L1 plus L2 plus L3. That's what we said from N4. Chapter 1, it can be a problem because it's a continuity, or rather, it's the revision of N4. Then we get our length total. Remember, then we get our length total. Then we said as a result of the force applied, the force applied will affect unit 1, will affect unit 2, will affect unit 3. Then we said in calculating the total change in length, then it will be total change in length equals to change in length on unit 1 plus change in length on unit 2 plus change in length on unit 3. But we said the formula of calculating the change in length when you are given the compounded material like this under the series connection, we said we will be using the formula looking at the Young modulus, looking at this formula. Young modulus equals to stress over strain. What is stress? It is force over area. What is strain? It is change in length over L original. That's what we said. Then from here, we are having strain equals to stress over Young modulus, and it is stress, it is force over area over Young modulus. Then here it is L. That's what we said. Then we are having area. Then here we are having area multiply by L multiply by Young modulus. Then we said under compounded material, this is the formula that we'll be using. It means here calculating the total change, it will be force applied. Which force? This force. It means it is force total. Multiply by length of unit 1 over area 1 of unit 1 multiply by E. For now, let's say we are dealing with steel. This is steel. This is steel. It means the type of material, it is the same. It means Young modulus, it is the same. Because we are dealing with steel, then the Young modulus, it is the same, or the strength of material of that compounded material, it is the same. Then it will be force total length 2 over area 2 multiplied by Young modulus. How are we then going to get the areas? Remember, you are given the diameters. You then have to make, it will be diameter squared pi divided by, then you get the area. This is the formula of calculating the area. Plus F total. Why F total? Because F total, that's the one that caused the change in this unit. Then L3 over area 3, Young modulus. This is the formula that we'll be using to calculate the total change in length. Okay? This is the formula that... Now, please. This formula does not limit you. What is this? What is this? If you are given stresses, you can always work out this formula from the stress perspective. You are now having stress 1, length 1 over Young modulus, plus strength 2, L2 over Young modulus, plus stress 3, L3 over Young modulus. It doesn't limit you. It will depend with the given formula. They can say calculate the total change in length, and yet you are given the stresses. It means this is the route that you need to take in calculating what? Your stresses. And again, under the series connection, the length can be the same. You can be given the length being of the same length. Here it could be 1 meter, 1 meter, 1 meter. It means the length it is the same. L1 equals to L2 equals to L3. Now, when coming to that formula, it will be x equals to x stress 1 over Young modulus plus stress 2 over Young modulus plus stress 3 over Young modulus. But under the series, it will depend with the given information. I hope you are with me, good people. It will depend with the given information, but nothing restricts you from playing with your formulas. Okay? Nothing restricts you from playing with what? With your formulas. Nothing restricts you at all. Now let's continue to explain this diagram. Let's continue. You are having this, it was compounded into 3. L1, L2, L3, D1, D2, D3. Now, in calculating the force total, you will calculate the force total from D3 because it is the smallest area in comparing to the other compartment. This one, it is the smallest area. It means the maximum stress will be calculated from unit 3. In calculating your stress, you will calculate it. It will be force total if you are given over area 3. If you are given the stress and they want you to calculate the force total, it means it will be force total equals to stress max multiplied by area 3. Okay? That's what we said from that diagram. And secondly, good people, you can be given a diagram in any shape. It doesn't matter. If you are given the diagram in this shape, you can tell that the smallest area it is that one. You can be given a diagram like this. Hollow, connected, hollow, connected. It doesn't matter. The smallest area it is that one. It doesn't matter how your series it is. As long as you are able to identify the smallest area, then you know that your maximum stress will be calculated from that smallest area. The force total will be calculated from that smallest area. Now, again, if you are given, let's say you are given that compounded material, but they want you to calculate the length or the diameter in unit 2. It means you will be given a change in length total. Then it will be FL1 force total over area 1 Young modulus. Then it will be plus X2 plus F total L3 over area 3 Young modulus. You will then calculate whatever that they want you to calculate from this change. From here, you will then have to make X2 the subject of the formula. You get the value of X2. After getting the value of X2, then you come and calculate whatever that they want you to calculate, be it the diameter. If they want you to calculate the diameter, that means here you need to make A the subject of the formula. After you've calculated your A, then you come and use that formula. Then you get your diameter. Or they can want you to calculate L. It means here you will make L the subject of the formula. Then L would be X2AE, isn't it? Divide by F. Then you get your L. Whenever you are given questions that they want you to calculate either length or diameter, you will always calculate them from the change. From the change. That's what you need to remember. Okay? Please don't forget that, good people. Can you see that our stress and strain, it is easy, it's just a revision from N4. But that which I said, it is exactly what you are dealing with here in N5. Don't make a mistake. It's exactly what you are dealing with here in N5. Okay, now let's make one emphasis, then continue with our notes. I'm sorry that this video, it will be lengthy, or I will make 2 parts video or 3 in explaining to you, good people. Okay, now let's look at this one again. Let's look at this one again. I want that if I'm done here, I know that nothing will make me to go back to this in explaining and say I forgot. Unit 1, Unit 2, Unit 3. Diameter 1, diameter 2, diameter 3, L1, L2, L3. Now we said it length total, length 1, length 2, length 3. Change total, change in length in unit 1, change in unit 2, change in unit 3. Now please, this can be steel, this can be copper, this can be aluminium. If that's the case, when coming to this formula, but the force would be the same thing, it will be the common. When coming to this, it will be force L, force total over area multiplied by Young modulus of steel. Area 1, length 1, plus force total, length 2 over area 2 multiplied by Young modulus copper, plus force total, length 3 over area 3 multiplied by Young modulus aluminium. You can be given different types of material compounded in series connection. But when you deal with them in calculating the total change in length, this is how you want to deal with them. This is how you want to deal with them. And nothing has changed. In calculating the change in x2, or if they wanted to calculate length 2d2, you do it exactly as I've shown you on the first part. Okay? Please don't forget this. This is what you'll be dealing with under your stress and strain. Now, this is the revision. Then I will send the stress and strain in chapter 5. We'll make it the two-part video. Thank you, good people.